In the previous video, we saw that the general solution to the non-homogeneous equation Ly equals f of t is a solution of the form c1y1 plus c2y2, where y1 and y2 solve the homogeneous differential equation, and a particular solution that solves the non-homogeneous differential equation. We made an educated guess at what our particular solution would be, but now I'd like to show you the general technique as to how we can guess particular solutions to the non-homogeneous differential equation. So we're going to start with a homogeneous differential equation, y double prime plus 2y prime minus 3y is equal to 0. Now, there's a characteristic polynomial that corresponds to this homogeneous differential equation, and that characteristic polynomial is lambda squared plus 2 lambda minus 3 is equal to 0. That factors to lambda plus 3 times lambda minus 1. And that tells us that lambda is negative 3 or 1. And since the characteristic polynomial has real distinct roots, our homogeneous solution is in fact y of t equals c1 e to the minus 3t plus c2 e to the t. Now we will use this homogeneous solution throughout to help us solve some non-homogeneous equations. So I'm now going to pose the non-homogeneous differential equation y double prime plus 2y prime minus 3y equals 4e to the 2t. Now you'll see that the left-hand side is the same as it was for our homogeneous equation. Okay, but now on the right we have 4e to the 2t. So I need to guess a particular solution so that when I take y double prime plus 2y prime minus 3y, I get 4e to the 2t. So the guess that I'd like to make for my particular solution will be a multiple of e to the 2t. I'll call it ae to the 2t. That's because if I take the second derivative of this function and then 2 times the first derivative of this function, and then I subtract this function, all of those are going to need to be multiples of e to the 2t if my result is going to be 4e to the 2t. So I'm going to now plug this guess into the differential equation. So I'll need to know what the first derivative is, which is 2a e to the 2t, as well as the second derivative, which is 4a e to the 2t. So if I plug that into my differential equation, y double prime is y double prime plus 2yp double prime, or single prime there, minus 3yp is going to equal 4a e to the 2t, that's the second derivative, plus 2 times, the first derivative is 2a e to the 2t, minus 3 times y, which is a e to the 2t. And that is supposed to equal 4e to the 2t. So now I'm going to add 4a plus 4a minus 3a. So that's going to tell me that 5a e to the 2t has to equal 4e to the 2t. In other words, 5a must equal 4, or A is 4/5. So my particular solution is in fact 4/5 e to the 2t. I would encourage you to plug this particular solution back into the differential equation and see that the left-hand side is indeed 4e to the 2t, which is on the right-hand side. So my general solution to this non-homogeneous differential equation is going to be y of t equals my homogeneous solution, which is c1 e to the minus 3t, plus c2 e to the t, plus my particular solution, which is 4/5 e to the 2t. So that's my general solution. It's the homogeneous solution plus the particular solution that I just found. So we're going to repeat this process with a few different functions on the right-hand side. So the next function that I'd like to try is going to be 27t squared. So again, I already know the solution to the homogeneous problem, so I need to make a guess for my particular solution. I can see that on the right-hand side, I have 27t squared. That's a second-order polynomial. And so the guess that I'm going to make is also going to be a second-order polynomial. In this case, at squared plus bt plus c. And the reason why I'm going to do that is because I'm going to be taking the second derivative of this polynomial, the first derivative of this polynomial, and also using a multiple of this polynomial. And so terms with t squared, t, and constants, like they're all going to appear in those derivatives, as you can see. Y prime in this case is going to be 2at plus b, and y double prime in this case is going to be 2a. Now I'm going to plug this in to the differential equation. So in this instance, we have that y double prime is 2a, and we're going to do 2 times y prime. So y prime is 2a t plus b. And then we're going to do minus 3 times y, which is at squared plus bt plus c. And this is all supposed to equal 27t squared. I'm going to expand out some of these terms, but I'm also going to write them in the order of the polynomial. So the first term is going to be the t squared term, so it's going to be minus 3at squared. The next term is going to be the coefficients of t. The coefficients of t are going to be, looking at this, they're going to be 4a. And then also looking at this, they're going to be minus 3b. All that's going to get multiplied by t. And then the constant terms that are left are 2a, and then looking here, 2b, and then looking here, minus 3c. Now that's supposed to equal 27t squared plus 0t plus 0, because there are no t terms and there are no constant terms. Now what I'm going to do is I'm going to match like terms. So here I'm going to get minus 3at squared is going to equal 27t squared. Well, that's going to tell me that essentially minus 3a has to equal 27, or a in this case must be negative 9. For the t terms, I have that 4a minus 3b times t has to equal 0t. So that tells me that 4a minus 3b must be 0. And that tells me that b must be 4/3 a, or 4/3 times -9, which is in fact -12. Now the constants tell me that 2a plus 2b minus 3c must equal 0. And that tells me that c, or must be one-third of 2a plus 2b if I'm solving for c. So in fact, I'm going to factor out those 2's. So it's actually 2/3 a plus b So in this case, that's 2/3 of -9 minus 12. -9 minus 12 is -21. And -21 times 2/3 is -14. So my particular solution, now that's all said and done, is going to be -9t squared, because a, the coefficient of t squared, is -9, and then -12t, and then -14. So the general solution is y of t is equal to my homogeneous solution, C1, e to the -3t, plus C2, e to the t, minus 9t squared, minus 12t, minus 14. So that's the homogeneous solution plus the particular solution. We're going to move on to the next example. In the next example, I'm again going to change the right-hand side of the differential equation. Now it's going to be 30 sine t. So again, I need to guess a particular solution. And the guess for the particular solution, I could do a constant times sine t, because of course derivatives of sine might look like sine. But in fact, the first derivative of sine is cosine. And so the guess that I'm going to make is a times cosine of t plus b times sine of t. That's because if I take combinations of the second derivative and the first derivative of this expression, it will have terms that look like sine t and cosine t. And in particular, I picked just cosine of 1t and sine of 1t because the right-hand side has just sine of 1t. If there had been a different coefficient of t, I would have included that in my guess. Okay, so in order to plug this into the differential equation, I'm going to need to know what the first derivative is. The first derivative for my guess, for my particular solution, okay, so this is my guess for my particular solution, is going to be -a sine t plus b cosine t. And then that's my first derivative. And then my second derivative is in fact -a cosine t, taking the derivative of -a sine t, And then the derivative of b cosine t is minus b sine t. Now I'm going to note, because it is really helpful, that this is in fact minus my particular solution. So the second derivative ended up being minus 1 times my particular solution that I guessed. So that when I plug into the differential equation, in fact, I have yp double prime plus 2yp prime minus 3yp is equal to, well, it's actually equal to 2yp prime, and then my second derivative, which is minus yp, I just proved that, minus 3yp is minus 4yp. And this will just make it easier to substitute in. Okay? So what is that going to end up being? So 2 times the first derivative of my particular solution, so 2 times yp prime, is indeed negative 2a sine t plus 2b cosine t. And then minus 4yp is minus 4a cosine t minus 4b sine t. Now, all of this is supposed to equal 30 sine t. And so all of this really equals, yeah, that's fine, 30 sine t. And then 0 cosine t's. So again, what I'm going to try to do is I'm going to match the sine t's and the cosine t's. So here, I'm going to notice that sine t appears here, here, and here. And so if I just match the coefficients of sine t, I'm going to have negative 2a minus 4b must equal 30. And then similarly, if I match the cosine t's, here I have 2b cosine t and minus 4a cosine t and then 0 cosine t. So that's going to tell me that 2b minus 4a is in fact 0. Okay, so when I match the sine t's, I got this equation. And when I match the cosine t's, I got that equation. So there are lots of ways that I could go about solving this equation. I'm going to go ahead and solve the red equation so that we can see that b must be 2a. And then I'm going to take that information and I'm going to plug it into the green equation. So that tells me that negative 2a minus 4b, which is also 2a, must be 30. So that's going to tell me negative 2a minus 8a is indeed negative 10a, and that's supposed to equal 30. So a must be negative 3. Well, if a is negative 3, then b, which is 2 times a, must be negative 6. So my particular solution in this case is going to be negative 3 sine t minus 6, negative 3, I got that wrong. A is the coefficient of cosine t, so negative 3 cosine t minus 6, that's b sine t. My general solution in this case will be y of t equals my homogeneous solution, which is c1 e to the minus 3t plus c2 e to the t, plus my particular solution, which is minus 3 cosine t minus 6 sine t. There it is. We're going to move on to the last example. The last example says to find the general solution of y double prime plus 2y prime minus 3y equals minus 8 e to the t. So this looks a lot like the example that we had done previously, where the right-hand side was 4e to the 2t, and we guessed a e to the 2t. So let's proceed in the same way. Let's go ahead and guess that yp, my right-hand side, is equal to a e to the t. That's really nice because, you know, the derivative of our particular solution is going to be a e to the t, and our second derivative is going to be a e to the t. So let's just go ahead and plug that guess in. Okay, so y double prime is going to be a e to the t, and then 2y prime, so 2a e to the t, and then minus 3y, so minus 3y is minus 3a e to the t, and that's supposed to equal minus 8 e to the t. So a plus 2a minus 3a is 0. But 0 is supposed to equal minus a e to the t. And something went wrong because that's not true. So what happened? Well, you'll notice that a e to the t was actually part of my homogeneous solution. It was one of the two solutions I found when I was solving the homogeneous problem right here. There's my a e to the t. So it doesn't surprise me that in that case, y double prime plus 2y minus 3 plus 2y prime minus 3y is indeed 0. So that means that I can't make a guess of a e to the t because a e to the t is part of the homogeneous solution. So I'm kind of stuck. What should I do? What should I guess for my particular solution? Well, let's try something that we did in the previous lesson when we had repeated roots of our characteristic polynomial and we only had one linearly independent solution, and that was to guess t times my previous solution. So we're going to try at e to the t. If we do that, my derivative is going to be, actually it's a times t plus 1 e to the t. Once I do the product rule and then I factor out e to the t. And then my second derivative, well, it's going to be yp double prime. And that ends up being a times t plus 2 e to the t. And that happens when I do the product rule and then I combine terms and I factor out the e to the t. So you can take a second and pause this video and compute those derivatives yourself, or you can just take my word for it. I'm going to plug that into the differential equation. It says that y double prime, which is a times t plus 2 e to the t, plus 2y prime, which is 2a times t plus 1 e to the t, minus 3y, which is 3at e to the t, must indeed equal negative 8 e to the t. So let's expand that out. That's going to be a t e to the t plus 2a e to the t plus 2at e to the t plus 2a e to the t minus 3at e to the t. Indeed, that's supposed to equal negative 8 e to the t. So I have an at e to the t and a 2at e to the t and a minus 3at e to the t. And those all end up canceling out. So what's left is 2a e to the t plus 2a e to the t, or 4a e to the t, is equal to negative 8 e to the t. That tells me that 4a must be negative 8, or a must be negative 2. So I've now found that my particular solution is c1 e to the minus 3t. Oh, sorry. I'm starting to write down the whole general solution. My particular solution is just negative 2t e to the t. You can plug that back into the differential equation and you can see that it works. So my general solution is once again my homogeneous solution. So that's c1 e to the minus 3t plus c2 e to the t. And then I'm going to add on my particular solution, which is minus 2t e to the t. And so this is the method of undetermined coefficients. In each one of these differential equations, I made a guess at the particular solution. It had a coefficient that I didn't know, say a, for example. In fact, actually, I made the guess here, okay? Or here, I made a guess which had 2 undetermined coefficients, okay? Or previously here, I made a guess that had 3 undetermined coefficients. Here, I made a guess that had just 1 undetermined coefficient. And then by plugging my guesses back into the differential equation, I was able to determine what the coefficients are. Now, I'd like to give you one word of warning, and that is that the general solution is always written down as the homogeneous solution with a C1 and a C2, and then the particular solution. And you must write it down this way before you ever consider initial conditions. So you have to write out the entire solution as you see it right here with the homogeneous solution plus the particular solution. And then once you've written that out, if you have initial conditions, you can solve for C1 and C2. It's very important that you don't try to solve for C1 and C2 just based on the homogeneous solution. You need to write out the entire solution with the particular solution, and then you can solve for C1 and C2.